to talk a little bit today about operating, I should probably even say very highly available multi-AZ applications. My name's Gavin McCullough. I've been lucky enough to be working at Amazon for just about 11 years now. I started off working internally inside our internal load balancer teams, operating DNS for Amazon, and then started working in Route 53, Route 53 Resolver, and Application Recovery Controller. And I guess the sort of common thread throughout all of this is that they're all very low in the stack type services. And they're all very critical availability requirements. So we spend a lot of time in those teams thinking carefully about how to build very resilient systems. So today, we'll talk a little bit about how we build resilient systems and hopefully give you some strategies to help you do that. It's important to note that not every service has the same resilience requirements. So you may well have applications that you're perfectly happy with their resilience already today, but then some customers we talk to really want to go the extra mile to shave every last minute off and make sure that they're as resilient as possible. So a lot of these strategies are really in that context. One of the things that I'm really excited about getting to do today is to talk about Application Recovery Controller's new feature that we launched just this week, which is called zonal shift. And the idea here is to be able to recover from any problem that happens in a single zone. So I'll talk a little more about that. I'm going to go through some strategies, as I said, for building resilient systems with availability zones. I'm going to talk about how AWS does that, and I'm going to go through a real-life example from AWS. And then we're going to talk through a demonstration where we use zonal shift on a toy application that you can download and use yourself and try it out. And then at the end, I'll just finish briefly with some best practices and how to think about using zonal shift in real life. So let's talk a little bit about building resilient systems and how to use availability zones as part of this. So you might not have predicted in advance that you would get a boxing quote on this, or even a fake movie boxing quote. But I actually really like, particularly the second sentence in this, I think it really gets to the point of how you think about building resilient systems. It's about how hard you can get hit and keep moving forward. If you build a single system with a single point of failure in it, as soon as that gets hit, you're in trouble. So you've got to think carefully when you're building a resilient system about what kind of failures you can tolerate and keep moving forward. So I'm going to start us off with just like a really toy, simple, obvious application, the kind of thing that we would have built as students and probably build now for a proof of concept. You just run the system on one server. And if I ask you what is the point of failure in this, what is the most obvious point of failure, well, somebody presumably will think one of those servers might fail. There's only one of them. We're going to have a problem. So a single source of failure for this system is a server failure. And typically, what you'll hear people say is single points of failure, and I'm consciously using the term single sources of failure here, because when you just look at the sort of map of the application on paper, you miss some of the sources of failure that are not actually one of the things on the map. So I'll get into that in a second. So let's solve the first obvious resilience problem. We want to be able to handle the failure of one single server. So we'll run our application across multiple servers. Makes sense, right? And so now, if the application is redundant across these servers, and we have enough capacity that if one server fails, the others can take the load, we're able to tolerate a failure of one host. And the next thing that we tend to think about is actually the human element coming in. So when you deploy this system, you're changing the code in some way. That is a pretty common point at which a failure will happen. And with a single system like this, if you think about it as a single system, you will typically relatively quickly deploy through all of the hosts. And if this is a bad piece of code, you may well have caused yourself a failure. Equally, if you're deploying to this system, and you make a config change, you will typically make it across all of the servers at the same time. So these two are single sources of failure that you do need to think about. And think carefully about, well, if I have a bad piece of code get deployed, maybe it slips past the tests, what's going to happen? And so the way we've kind of come to over the years to handle these situations is to really break the system out into replicas. And the idea here is that we don't really want to do one deployment to the whole system, which could cause it to fail. So the way we will orchestrate our deployments when we have replicas like this is we're aiming for, if there's a bad deployment or if there's a bad config change, we only want it to impair one replica at a time. So we will fully deploy replica A, run a bunch of tests on it in production, make sure it's good, and then we'll move on to B and C. And the idea here is that if there is a problem in that deployment, replica A can be easily removed from service. And so even if we have a bad deployment, we can recover from that very fast. Rolling back a deployment itself can sometimes take quite a long time. So just being able to remove the replica from service gives you the ability to recover very quickly. Similarly, when we're running replicas like this, our operators think carefully about this as 3 different subcomponent services, so that if they need to make a config change at some point, they don't make it across all the replicas. They make it to one replica first. Observe, make sure everything is good, and only then do they touch the other replicas. So let's move on in our sources of failure list. We could have a local network issue. This is one data center with all of these replicas in it. We could have some other infrastructure issue, maybe a power problem. There's a variety of things that can happen. And so this is why AWS, long time ago, started offering availability zones. The idea being that if you're building multiple replicas, you want them to be as independent as possible. The idea really here is, I only ever want to see one replica fail at a time because I know how to deal with that problem. And so by siting them in different availability zones, which are different data centers distant from each other, we're able to tolerate, or we're able to be sure that if replica A experiences an infrastructure problem, it's very unlikely to be touching B or C, and we can just take replica A out. Now, at the really advanced level, over time, as we've kind of looked at these events, we still start to identify other things that can cause more than one replica to fail at a time. And some of the techniques that we've gone into, which, like I say, you probably wouldn't do up front, but are things to think about later. You start seeing, okay, well, we had multiple replicas fail because they all hit the heap memory exceeded limit at the same time. And so we even start diversifying things like that across the replicas to say, well, we'll have one replica that has a lower heap memory limit than the others. And if we ever hit that limit, we'll only hit it in one zone. We'll take it out, we'll fix it. And meanwhile, the other 2 have a higher limit and can move on. We've even done TLS cert expiry different in each AZ. If we're ever caught with a TLS cert expiring, it only impairs one AZ and we can recover immediately. Now, it's important to say that this won't solve absolutely every possible problem, right? And we're largely talking about the stateless application layer. There's probably a database behind there. It's going to have to be consistent across them. And so you have to be very careful about those remaining sort of single sources of failure for the application. If you're updating your database schema, you really have to do that in one place. So just to give an example of a real-life system that is like this and very visibly like this in public, if you've ever used Route 53 and you create a hosted zone, you get given 4 name servers. The 4 name servers live on, you'll see their names and com, net, org, and co.uk. And what that's telling you is which of our replicas they're running on. And the way we think about this is exactly what I'm talking about. So when we do a deployment, we will do all of the com pops. There are about 50 of them worldwide. We will deploy all of com, do our tests, make sure everything's good, and only then do we begin deploying on net. And the purpose of that is that as a customer, wherever you are in the world, at most we might impair one of your, in an unusual deployment problem, we might impair one name server, but never all 4 at the same time. And typically DNS resolvers will handle that very well. So if you look at a map of the world, you're located somewhere in here. Your DNS resolver is able to talk to the nearest red, green, yellow, and blue pop. And we're only ever touching one of those at a time. So I've talked a lot about redundancy, about having multiple replicas. I haven't talked yet about how you actually handle failure. The way a DNS resolver would do it is typically just retry all 4 very quickly. And so you can have one of your name servers not responding, and a DNS resolver will really just make that a non-event. But for web applications, you typically need to do something slightly more sophisticated. So this is a fairly standard application architecture that probably a lot of you have used. It's an NLB with a set of EC2 instances in 3 zones. And so there's a bunch of failure handling already built into this out of the box that you don't need to do. So the NLB will be probing your instances, running health checks against them. If one of them stops answering within a minute or so, NLB will detect that, remove the host from service. Very simple failure handling. If you have a more severe event, perhaps on one replica, the NLB itself might say, okay, all the instances aren't answering, at which point Route 53's health checks will kick in. It is running health checks against each of the NLBs in each AZ. And if one of those NLBs stops answering, it'll be removed from DNS very quickly. And so it's very easy, or it's tempting, to look at these kind of situations and say, well, these are all hard failures. They're relatively easy to detect. A host is unresponsive. The application's not running yet. Excuse me, the application has stopped on the host. Maybe even the load balancer is not responding. These are easy to detect type failures. But there are a sort of second class of failures, which we tend to call gray failures. So it's easy to ask what happens when X is down. It's a very obvious question to ask. The harder question that sometimes you don't think about until the real event comes is, well, what happens when X is still up, but it's impaired? Maybe it's slow, maybe it's intermittently failing or giving bad answers or something weird like that. And these are hard things to health check for, being honest with you. So there's a variety of causes of these. A software deployment is a classic. The new version of the software is crashing and restarting regularly, impairing customers, but it's answering enough of the health checks to stay in service, so it stays in. Maybe you make a bad config change, same kind of thing can happen. You can have reduced capacity in one availability zone, where the remaining capacity is just about able to keep up enough to answer the health checks, but it's not really doing a good job with customer traffic. Again, these are all gray failures. And another one that's common, or that's not very common, but can happen, is packet loss, which will slow down communication between applications. And again, health checks may not be able to actually determine these. And so the sort of surprising outcome of this is that a more severe failure is actually better for you because it's easy to detect and remove, and that will just be automatic. But if you're really, really trying to shave every last minute off recovery time all the time, and you really have very strong resilient goals, you start to worry about these gray failures because they're the ones that will last a bit longer. The other thing is that gray failures are actually subjective. So if I said to you, if there's a gray failure in an application and we add 50 milliseconds of latency to the responses, is that going to be a problem? For many applications, the answer is probably not. But there will be some applications for which an extra 50 milliseconds is a serious problem and the client is unable to keep up now because of it. So like I say, these are really kind of ambiguous and hard to deal with. And so what we're trying to talk about here is a set of strategies to handle these gray failures. And the high level kind of what we're trying to do here really is to turn the gray failures into hard failures, to like be able to rethink them as hard failures and handle them. And I have 3 complementary strategies to talk about. You can use potentially all of them or only some of them. The first one, how many people have heard the term deep health checks? Hands? A few? I mentioned before that the network load balancer or application load balancer are regularly sending your host a basic API call. And if you respond with a 200, you'll stay in service. If you don't respond or you respond with 500, it'll call you call that host unhealthy. And the obvious thing to do when you're writing the application is to just do something very, very simple and just respond 200. And that's useful. That's what we would call a shallow health check. It is useful. It means that the network load balancer knows that the application is running, that it's listening on the right port, and this host at a basic level looks healthy. But that host might have a full disk or be unable to write to the disk. And there may be 100 other reasons that host is not healthy right now, but the network load balancer doesn't know that. And so one thing that you can do that's relatively cheap is to start adding, is to customize that health check handler in the application to test the host more thoroughly and make sure that it really is healthy. The downside of this is you got to be really careful what you test. So it's very easy to say, well, I will just test every possible, like I will do everything that the host needs to do. The challenge is that you probably don't want, there are probably some failures that you don't want that host to take itself out, because the same thing's happening on all the other hosts as well. And so you don't want a cascading failure on your hands. The other thing is that there are some types of gray failures that you can't really detect on a host as well. So, for example, if there's packet loss between the load balancer and the host is not going to detect that, or may struggle to detect that. If you're interested in doing deep health checks, looking into deep health checks more and doing this, I would really recommend the Builders Library article that David Janacek wrote on this topic. And he talks through all of those trade-offs that I'm mentioning. So the second strategy, or the second useful feature, which was literally launched last week by ELB, is a very specific case of handling one gray failure and turning it into a hard failure. And it's to set, per availability zone, the minimum healthy targets. So a picture makes this much easier to understand. So let's say we have this application. We have 3 hosts in each AZ, and we're getting more or less even load in each availability zone. Now, suppose something happens like that. 2 out of the 3 hosts have failed in AZ3. So now, the AZ still looks healthy, so 1/3 of the traffic is going to each availability zone right now. And now that one host is having to handle 1/3 of all traffic, while the other 6 healthy hosts are handling 2/3. So there's, this can cause, maybe that host is just unable to keep up with that load. That's likely. If it was able to keep up, then I'm not sure why you had 3 hosts in the first place. So this is another form of gray failure. That host is probably limping along, slowly handling what requests it can and dropping some. But if we set minimum healthy targets to be 2, then NLB will automatically say, this AZ is down, take it out of DNS, when we drop below 2 hosts. And this basically turns what was today a gray failure into a hard failure. We no longer need to worry about this case at all. So this was, as I say, launched last week for both application and network load balancer. It's especially useful with when cross-zone load balancing is off. I will talk a little bit more about cross-zone load balancing in a minute. But effectively, really, just what you're doing is saying an AZ is not healthy unless it has a minimum number of hosts. So the third strategy, which is really the meat of this talk, is detecting a bad AZ or a bad zonal replica and shifting away from it. And so there are a myriad of possible ways that one zonal replica might have a problem, and we're really turning them all into a failure mode that we know, which is one zonal replica out of service. And so we can simplify all the possible failure modes in one zonal replica. If the failure is contained to one replica, we just take it out. And we can easily test that situation in advance. And we use this really widely within AWS. So I have kind of 3 steps for how to do this. The first one is to turn off cross-zone load balancing. And the idea here is really to establish our zonal replicas. So keep them apart and don't exchange data between them. So if we look at this picture here, this is the standard with application load balancer, the default out of the box. And you can see here that the clients do a DNS lookup and they hit a load balancer in one availability zone. But the load balancer is then entitled to send the traffic to any of the AZs, to a host in any AZ. And this is good in ways. It will give you smoother load balancing because the load balancers are in line and able to make better decisions than DNS. And if one load balancer for any reason should briefly fail, you'll still have all of the hosts taking traffic because the other load balancers can send to all hosts. But the downside is that the replicas, the individual independent replicas are not very well defined here. And if you want to test and identify a problem in a single replica, it's quite hard to do here because whichever load balancer you hit, it's sending traffic to all AZs. So turning cross-zone load balancing off looks more like this. If you hit the IP address of the load balancer in AZ1, you know you're hitting the instances in AZ1 as well. So it makes that detection much easier. And it also reduces the interactions between AZs. So to some degree, at least for this strategy, I'm suggesting you may want to turn cross-zone load balancing off. If you're going to do that, if you're going to follow that advice, there are a few things to think carefully about. It effectively means that the amount of load that shows up in each AZ on your hosts is dictated by DNS. So that's something to think about. You might get slightly more unevenness in load between the hosts depending on how many clients you have and how they behave. For a large application, it's usually pretty straightforward, but for a small one, it can be, you might have just one whale client and they may just show up in one AZ. You should also make sure that you have equal capacity in all AZs, because if you're anyway large, you're going to see all the traffic evenly spread over the AZs, and they can only go to the hosts in the local AZ. So if you have 3 hosts in one AZ and 1 in each of the other 2, you really need to even that out before you turn off cross-zone load balancing. The ELB team tends not to recommend this for very small target groups. So if you only have 1 or 2 hosts behind your load balancer, you may or may not, you may want to think carefully about this. If you have a bigger application, it's usually pretty safe. I mentioned before the minimum healthy targets. That's definitely something to think about using if you're turning off cross-zone load balancing. And something that I think, if you've talked to your solutions architect within AWS, you'll have heard this before, but you really should provision enough capacity to handle one AZ just disappearing temporarily. And if you think about it, that is literally what we're going to plan to do. So if you're following this strategy, you really, really need to make sure you have enough capacity to sustain loss of one AZ, because we're going to deliberately take one out. So returning to the overall strategy, steps B and C are monitor the customer experience in each AZ explicitly. So we want to be able to tell when one AZ is not operating perfectly. So the first thing you can do, most people's applications will post metrics either to CloudWatch or to maybe Grafana or whatever you're using. Whatever your metric system is, you probably want to adjust those metrics to add the AZ that the host is posting from as a dimension of the metrics. And that allows you to see how many fatals there are being generated in each AZ, what the average latency is in each AZ, what the P99 latency is in each AZ, and generally to start comparing the AZs in order that you can see a problem AZ if one arises. A thing that we find really helpful to do is to run what we call canaries. And recently, CloudWatch brought out a product for this, to do this in a managed way called CloudWatch Synthetics. So basically, Synthetics allows you to write a small piece of code which will be constantly making calls against your endpoint. And so a typical ELB, you'll get a DNS name like that, and you might give it your own public name, obviously. But they also provide these zonal DNS names. So if you want to run a canary against AZA only and just see how well requests in AZA are working, you can use that second line, and the same for 2B and 2C. So you can actually run canaries against each AZ individually and compare them. And I'll show in a picture in a minute or two how beneficial that is. So looking at our architecture, what we're going to do is we're going to set up a CloudWatch Synthetic running individually against each AZ. And because we want to understand the customer experience, I'm going to set a fourth one up which just does what customers do, hit the AZs at random, so that we know what the customer experience looks like. So now, at this point, we have 3 different ways to potentially see a problem in an AZ. The first one is have passive monitoring on our hosts that are posting per AZ. The second is we'll have active monitoring each AZ, sending requests to it, and timing the result. Equally, if there is an infrastructure problem within AWS in one AZ, we'll typically post that to the health dashboard, so you can see that potentially as well. So when we determine that there is a problem with one of our zonal replicas, the next step is to take that zonal replica out. And this is the kind of new part of this. So what Application Recovery Controller Zonal Shift offers you is the ability to temporarily say, steer traffic away from that AZ for now, please. I have some problem there. Maybe it's because there's a deployment ongoing there that's not going well. Maybe it is an infrastructure problem. Whatever it is, you can just ask, shift away from that zone, please. It's one simple API call that we've designed to be very reliable. So even during events, you should be able to call this and say, shift me away from that AZ, please. And this is included out of the box in every ALB and NLB where cross-zone load balancing is turned off. So you don't have to set anything up, it's already there. And it costs nothing. We don't charge for the existence of the control, we don't charge for making calls to it. So the API call itself, just showing it here using the CLI, we use ARC zonal shift. We deliberately have a different API for this. And you make a call to start zonal shift away from AP Southeast to AZ1. We're using AZ IDs here, not the older AZ names, because AZ IDs are the same for everyone. And if you have multiple accounts to deal with, you want it to be the same across them all. We have an expiry time here, and this is kind of important. I said that AWS has been doing this for quite a long time, and one of the lessons that we learned is it's really not a good idea to allow a shift or to forget that a shift is in place. You really need to return to your fully redundant form as quickly as possible. So we've deliberately built in an expiry time into this. Then, of course, we specify the actual load balancer that we want to apply this to. And we have a comment just for convenience so that we can look back and see what happened and why we did it. And the only thing from the response that's really important is the zonal shift ID. You can do this in the console, obviously. So we have a console for this. This is a small page. I don't have a lot of load balancers, but down the bottom you can see the resources I have. And this is looking at one resource, and I can click Start a Zonal Shift, choose the AZ I want to shift, set an expiry time, and acknowledge it. And that's pretty much it. So what actually happens when I enable a zonal shift? So in steady state, your application is taking, clients will connect to one AZ or another. Some clients will connect to this AZ, some will connect to that AZ. And so what you're seeing is in steady state kind of traffic just evenly distributed over the AZs. Now, before we apply the zonal shift, we really do need to make sure that we are redundant to one AZ going out of service. So we need to make sure that we have 50% idle headroom in each AZ. Because when we take one, the load will be roughly evenly distributed over the other two. We also need to make sure that all of these AZs are healthy and taking traffic. If one of the AZs is unhealthy right now and we're not aware of it and we try and take another one out, we may surprise ourselves and not have enough capacity. So it's important to know that all AZs are healthy and taking traffic. Obviously, we have cross-zone load balancing disabled. And now we're going to monitor the success rate in each AZ using the techniques I talked about earlier. So they're about even right now, which means the aggregate success rate for customers is roughly the average of each AZ, and everything's looking fine. So let's say an event happens. Maybe a deployment is happening in AZ3, don't know. Something has happened in AZ3. The success rate has dropped, and that's having an impact on the customer success rate, the aggregate success rate as well, right? Because it's an average of the three. So I'm going to start a zonal shift. And what that's going to do is slowly, over a few minutes, traffic will start to drain away from AZ3. What we've actually done is remove the IP address of AZ3 from DNS. And so clients will continue until they close the connection. Typically, that will happen over a few minutes. So a few minutes later, we'll basically see all the traffic, extra traffic going to AZ1 and 2, and practically nothing going to AZ3. We're still seeing the success rate is down in AZ3, but the customer success rate is back up to normal. So we have mitigated this problem. We don't actually know what the problem is yet, but we've been able to mitigate it. And this is the real power here, that we didn't have to spend all the time, look through all the logs, understand what the problem was to fix it. We just shifted away. If it takes us some time to understand and fix the problem in AZ3, we can extend the zonal shift, that's no problem. And eventually we figure out what the issue is. We get the success rate back up to normal in AZ3, we're comfortable, and so we end the zonal shift with a cancel zonal shift call. And things go back to normal. So zonal shift, like I say, allows you to temporarily shift traffic away from one AZ, and the real purpose of it is to cut down the time it takes you to recover from one problem in one zonal replica. It's available in preview now as of Monday in 9 regions. Obviously, we'll add the other regions in due course. And if you're interested to look at it, there's a blog post that we posted along with this. So I said that we use this in AWS a good bit. And so I wanted to actually prove that with some real-life data. Zonal Shift itself is a new product, new thing that we've built, but the technique internally has been used in various ways within AWS for as long as I've been at AWS. And so this is a service running in one of the AWS regions. I've had to remove some of the data in order to be able to show it to you. So, but what we're looking at here on the y-axis is the bits per second going through each AZ, somewhat normalized. And then on the x-axis is time. And so this is a graph of one of their callers who will post errors if there's any problem calling that service. And so as we move time on, something happens, and that customer service starts saying, I'm seeing errors now. And meanwhile, the team themselves are getting alarms. And they have specific alarms on each AZ, on problems in each AZ. So they're immediately confronted with pictures like this that say, 2 AZs look normal, 1 AZ looks bad. And so they pretty quickly go, okay, we've got to solve this problem. Simplest thing to do, we know we have enough capacity, we're just going to take AZ-A out. And so they do that. And so you see the load increase in B and C, and the load drop to 0 in A. And the customer experience recovers immediately. Now, they still don't know what the problem is. And so over the next period of time, they're working away, looking at logs, understanding, and they realize, oh, there's an automated deployment has happened in A. They do all their deployments 1 AZ at a time. They're automated. They obviously have tests beforehand, but something has slipped through in this case. And so without actually knowing that there was a problem, they fixed it for customers, and now they're actually digging into the root cause. So they roll back that deployment, restore order in AZ-A, and return it back into service. Now, if you look at this timeline, the actual customer impact was only 10% of the overall event. So they cut down the time to recover very substantially here. So this is an example of an AWS service that is applying this strategy. They deploy 1 AZ at a time very consciously. They monitor each AZ individually. And when there's a problem in 1 AZ, they can just take it out. So I wanted to demonstrate a little bit more how you would use zonal shift in the real world yourselves. So there's a CloudFormation stack that I've published on GitHub, which I'll show you the URL now in a second. But it's basically the architecture we've been looking at. A 3AZ NLB, cross-zone load balancing is off. And we have an auto-scaling group with 6 instances. They're just running the Apache web server with a file they can serve. It's kind of a toy thing. And then we have CloudWatch synthetics canaries running against each AZ. And they have alarms on them, and then we have a regional one to monitor the customer experience. And we've built a CloudWatch dashboard as part of this CloudFormation template. And we've added in some extra fault injection simulators so that we can actually create gray failures and see what happens. If you want to do this yourself afterwards, you can use that Git repo to take the CloudFormation template. Everything pretty much is in there, including the chaos testing. And you can load the stack with that fairly simple command. Pause there in case I see people are taking pictures. Okay. So back to our architecture. We have monitoring running against each AZ individually, and a customer monitor running against all 3. And so the dashboard looks like this. So what you see is this has 4 columns. The first column is giving us metrics on the real customer experience. And so we have a canary, an alarm based on the canary results, and the latency that the canary is seeing on the customer endpoint. We can see the response codes that the canary is seeing. So it's all 200s right now. The 500s and 400s are at 0. Good story. We have no unhealthy hosts across the region right now, and the traffic level you can see. And then these other columns are deliberately designed that we can look at each AZ individually. So this is AZ1, all the same metrics, no unhealthy hosts, taking a portion of the traffic, AZ3, and AZ2. And so I'm going to inject a hard failure here. And this is one that we expect ELB to handle automatically for us. So I'm just going to stop the web server in 1AZ on all the hosts. So our picture again is like this, and we're going to use Fault Injection Simulator to just jump in and stop Apache. So with Fault Injection Simulator, I have a couple of templates there. I can just list them and start one of them. At the start of the experiment, we can see there are 3 IP addresses in DNS for our NLB. And that the dashboard is largely clean. All AZs look the same. Now, about 3 minutes later, this is what you see. So the first thing to look at is that AZ3 is now in alarm. The other 2 AZs aren't, and the customer experience isn't. And we've stopped getting canary response time data there. You can see that line is pulled back a little bit because we haven't had data for a few minutes, which is, I think, why it's in alarm. And if we look at the unhealthy host count, it has risen in AZ3, and the overall regional number has risen as well. But the other 2 AZs are looking fine. And now the NLB processed bytes, you can see that AZ3, understandably, we've stopped Apache, has basically dropped to 0. And the other 2 AZs initially had a dip, but then have recovered and are actually taking more traffic than before because AZ3's traffic has been redirected away. All except the actual canary that we run on AZ3 because that naturally just keeps running against AZ3. But the key point here is that the customer experience hardly noticed. ELB automatically handled this failure for us. And so if you have an application or a deployment going in a single AZ and it stops the hosts, ELB will automatically kick in and solve that problem for you. Your alarm goes off, go in and fix it, while customers don't know. So during this event, we're seeing that DNS has dropped to 2 IP addresses. And what's happened is all the hosts failed in one AZ, and so NLB signaled to DNS, take this IP address, this AZ out of DNS. So as we roll on the time, and eventually I say, okay, I've had enough of this, I just kill the 2 hosts, terminate the 2 hosts in AZ3, and let auto-scaling replace them for me with running Apache instances. And we start to recover, and traffic goes back to normal. But this event lasted 3 minutes, even though I didn't really fix it. So now the second type of failure that I've been talking about is gray failures. And so I'm deliberately here designing a failure that I kind of know the health checks won't work for because packet loss is a really difficult type of gray failure. So what I'm going to do is I'm going to take 1 AZ and I'm going to inject packet loss into it. So again, looking at our CloudWatch, at our architecture, we're going to use Fault Injection Simulator and create packet loss just in 1 AZ. So we start off, we have 3 IP addresses in DNS. We're going to start our experiment, and we see dashboard clean at the start. A couple of minutes later, we start to see a rise in latency. And so the customer experience is seeing this latency, and AZ3 is also seeing the latency. AZ1 and AZ2 look perfectly clean. So it's really fairly evident here that AZ3 is the problem. But the canary response codes are the same. This is a gray failure. According to the health checkers and anything that's looking just at response codes, everything looks fine. All the hosts are healthy. Traffic is evenly spread across the AZs. Now, like I say, this is a gray failure. So in many cases, for some customers, this is just fine. They just wouldn't worry about it. But for some customers, this is a sensitive issue. They're seeing sporadic high latency, and their callers, this may be a real problem. So for them, you can, for those people running who need that and need to be able to recover from this, you can now use zonal shift to be able to just say, take AZ3 out temporarily for me. And so, about 2 minutes later, we start to see that DNS is now only 2 IPs instead of 3. One of the AZs is now out of service. And so, within a couple of minutes, up in the top left there, you can see the regional canary alarm is now green again. And the latest data point on that latency graph is back to normal. AZ3 is still showing the problem. We haven't actually fixed it. We've just shifted away. And as we roll the time on, you can see that further down, the traffic is starting to shift away. So our latency up the top, AZ1 and 2 are normal. AZ1, the customer experience was impacted for a bit, we did the shift, and we're back to normal. So the impact time is really those few data points. And AZ3, we haven't fixed it yet, still has the problem. Again, all of the requests and responses are working, the hosts look healthy. But the traffic has been shifted away from AZ3. We're still seeing some traffic in AZ3, which is basically our canary that's running direct against that AZ. But all the customer traffic has shifted away to 1 and 2. And so I set the experiment to run for half an hour, so it ends of its own accord, and you start to see AZ3 back to normal. And we can stop our zonal shift and move back into AZ3. So again, I appreciate these are kind of toy experiment things where we've just made up a gray failure, but these things are real, and it gives you the opportunity, without actually having to dig into what the cause of the failure is, to just say, I can see it's only one AZ, I'm just going to shift away, and then I will look at the problem with customers already mitigated, everybody happy again. And this takes a lot of pressure off you as an operator to not make rash decisions. When you know the customers are fine, you're just down one AZ. So in this case, we've reduced the time by about 75%. Admittedly, it's a toy experiment, but still. So last thing to talk about in this talk is just to give you some best practices for how to think about this. One of the things that you have to be careful with is you're deliberately going to take capacity away from your application. And so you need to think really carefully about that is a safe thing to do for you. So the first best practice here, which I think I've already talked about, but I'll elaborate on just to make sure it's clear. You really want to make sure that you have enough capacity in the remaining 2 AZs to immediately sustain the load when 1 AZ goes out of service. That's a general best practice in AWS anyway, but particularly where you're going to plan to remove 1 AZ. You could use auto-scaling for this and expect the auto-scaling group to handle it, but that will take some time. The other thing is that you've got to be careful if you're using auto-scaling. The typical auto-scaling pattern is to use the CPU utilization averaged over the 3 AZs. Now, anybody see a problem with that? What's going to happen is you're going to drop the CPU utilization in 1 AZ right down, and you're going to rise it in the other 2. And the auto-scaling group is going to go, nothing changed. So auto-scaling may not react. You need to be careful and think that through. The other important thing is to make sure that your zonal replicas are actually healthy. If you saw on the dashboard, we had the number of healthy, unhealthy hosts on there very deliberately. If, for the sake of argument, it is possible to set up a load balancer with all hosts unhealthy all the time, maybe your health check handler is actually broken. An ELB will do the best for you and say, well, having no hosts up is probably not a good thing, so they'll fail open and just send traffic to all the hosts. But it does mean that you can end up in a situation where you don't realize that you're unhealthy everywhere. So you need to be a little bit careful with that. And actually, having a dashboard that shows you how many hosts are unhealthy is a pretty good way to handle that. If you are unhealthy in every AZ, zonal shift is going to try to mark 1 AZ unhealthy, and they're all unhealthy, so it won't do anything. The other thing that's really important is to test this in advance. So again, we're going to take a whole AZ out of service. And you probably don't want to wait until the real event when you need to do it. You need to do this in advance and know that it's going to work for you. So probably do it in your test environment, your Gamma, whatever you have. And then maybe take a low time and do it in production. Then maybe take a high time and do it in production. And really build the confidence to know, I can do this anytime. I would tend to recommend, for best practice, use the API or the command line interface. The console is there, it's pretty good, but in real events, you want to take the minimal dependencies possible. So the command line interface is very, very simple, has very, very few dependencies, and it is the most reliable way to do this. It's important also, I kind of alluded to it earlier on, to think carefully about this as a temporary action. You don't want to be running with 1 AZ out long term. And so that's why we've built the expiry time into it. The quicker you get back to all AZs back in service, the quicker you're back to redundant, and if coincidentally some other thing happens, you're ready for it. And logical thing to say when you look at this is, I don't want to do it manually, which is totally fine. You want to automate that. But think very carefully through the edge cases. So for example, you could see a large increase in traffic across all 3 AZs. You do not want your automation to kick in and take one AZ out of service in that situation because it's just going to make the problem worse. So you need to think carefully. Typically what we've found is people will use this manually for a while and get the hang of it and start to understand the edge cases themselves intuitively, and then they'll move on to automation. But if you want to automate this, that's fine. There's an API for that purpose, but just think carefully about those edge cases. We built a bunch of active monitoring against each AZ, and that's really, really useful. If you're really striving for the absolute best practice here, I would run the monitoring in a different region, because that will give you a better picture of the customer experience coming in from the outside of the region. It also decouples your monitoring from the application itself by running them in different regions. So you may not necessarily want to do that, but it's potentially a thing to think about. So just summarizing overall what we've just discussed today. So the idea here is we try not to build one system, deploy one system, operate one system. We try to build multiple redundant full systems, deploy them separately, modify them separately, think about them separately, monitor them separately, because that allows us to recover when one of them fails. And in AWS, a lot of the time, we will have obviously run each replica in different AZs, and we will even go as far as varying limits and trying to make things work differently in little ways in each AZ. Occasionally, people even talk about running different code bases in each AZ. To be honest with you, that's a bit on the expensive side even for us, but it is the kind of thing is to do everything you can so that when you see a failure, it only happens in one AZ and you can just recover quickly. And ELB's health checks will do really well for this, will automatically mitigate all of the hard failures. If you use minimum healthy targets, you can even turn some of the gray failures into hard failures. And for the remaining ones, the kind of hard to catch ones, you now have ARC zonal shift, and you can just say, yep, take me out of that AZ. I see I have a problem here. Move it out. If you'd like to read more on zonal shift, you can see more on the Application Recovery Controller website, or you can look up the blog post that we launched on Monday. And as I say, there's a CloudFormation template linked from the blog post, so if you'd like to take this away, launch that CloudFormation template, run the experiments yourself, exactly what I did here, that's all available there. And thank you all very much, especially for coming all the way out to hear this.